All right, we are here for another lesson in Algebra 2. This is our last set of notes for the semester, so that is exciting. Today we are going to be talking about complex numbers. So, up to this point in your math career, you have always been told that you cannot take the square root of a negative number, and in problems where we got square roots of negatives, we wrote our answer as no real solution. This is still technically true. There is no real solution. However, the answer no real solution is no longer going to be acceptable because today I'm teaching you how to write imaginary solutions. So we are going to let the letter I for imaginary number represent the square root of -1. So I is always going to be the square root of -1. And if I square both parts of that, I get I squared and my radical goes away. So I've got I squared equals -1. So these are the two expressions we're going to be using today to talk about our imaginary numbers. So if I have the square root of a negative number, I can rewrite that as the square root of the number times the square root of -1, which becomes the square root of that number times I. And if I can reduce this radical, I will. So what are complex numbers? Complex numbers are numbers that have both a real and imaginary component. And so our standard form for a complex number means the real number always goes in front and the part with an imaginary number goes in the back. So let's look at some examples with imaginary and complex numbers. Starting in example set 1, part A, I have the square root of -4. Now I can rewrite that as the square root of 4 times the square root of -1. And we established in the beginning that the square root of -1 is I. So this is the square root of 4I. Now, 4 is a perfect square, so I can actually reduce this to be 2I. And that is how we represent the square root of -4 as an imaginary number. Let's do this again on part B. I've got the square root of -4 over 25. Again, I can rewrite this as the square root of 4 over 25 times the square root of 1. And we know that we can allow the square root of -1 to be represented by I. And the square root of 4 over 25 is a perfect square, so this is going to become 2/5 I. And there is my imaginary solution. Okay, let's look at C. I've got negative square root of 49. That is the square root of 49I. I've got minus the square root of -9. That's the square root of 9I. And plus the square root of -36. That's the square root of 36I. So simplifying all of these, I get 7I minus 3I plus 6I, because those are all perfect squares. Now, these are like terms. Just like if I had 7x minus 3x plus 6x, I could combine this by adding and subtracting my coefficients. I can do the same thing here with I. So 7 minus 3 plus 6 gives me 10. So this is going to be 10I. Okay, let's look at D. Again, I am combining like terms when I can. 6 plus 3I and 2 minus the square root of -8. I need to rewrite this in terms of I. So that is going to be 2 minus the square root of 8I. And I can simplify the square root of 8. It's going to be 2 square root of 2I. And now I'm going to combine my like terms. My real numbers, 6 and 2, make 8. And that always goes in the front. Now, my coefficients on my I terms, 3 and minus 2 square root of 2. Those are not like terms, so I'm going to have to leave them separate. So I'm just going to subtract those two, 3 minus 2 square root of 2 times I. All right, on E, I'm squaring a binomial, which means I'm foiling. So 3 plus 2I times 3 plus 2I. 3 times 3 is going to give me 9. 3 times 2I is going to give me 6I. 2I times 3 is going to give me 6I. And 2I times 2I is going to give me 4I squared. So I have 9. I can combine those middle terms. 6I plus 6I will give me 12I. And then I have 4I squared. Remember we said at the beginning that I squared is -1. So that is going to be 4 times -1, which is -4. So I can combine the 9 and the -4 to be 5. plus 12i. And there's my final answer. Again, the real number always goes in the front when we have a complex number. All right, example F. Again, I'm foiling here. 8 times 12 is going to give me 16. 8 times negative 5i is going to give me minus 40i. 3i times 2 gives me 6i. And 3i times negative 5i gives us minus 15i squared. So again, I can combine my middle terms to get 34i, and then negative 15i squared. Again, I squared is equivalent to negative 1, so that's going to be negative 15 times negative 1, which will become positive 15, and I can add 15 and 16 to get 31 minus 34i. Again, the real number always goes in the front. Okay, we are going to shift gears slightly now and talk about patterns of I as they relate to exponents. So let's look here at these exponents. Quick refresher on exponent rules. If I am multiplying like terms, such as x squared times x to the third, I add their exponents. So that would be x to the fifth. So when you're multiplying like terms, you add their exponents to get your final result. So we're going to use that exponent rule to look at this pattern here. Okay, starting with I to the first power. That is just itself. Anything to the first power is itself, so this is just going to be I. I squared, we already know, is negative 1. And then if I have I to the third, that's the same thing as saying I squared times I to the first power. Again, because I add my exponents, 2 plus 1 would give me 3. So this is negative 1 times I, which is negative I. Now let's look at I to the fourth power. That would be equivalent to saying I squared times I squared, which would be negative 1 times negative 1, which is positive 1. Okay, on to I to the fifth. That would be the same thing as I to the fourth times I to the first power. So that's 1 times I, which is I. Okay, what about I to the sixth? That's the same thing as I to the fifth times I to the first. Well, that's going to be I times I, which is I squared, which we already know is negative 1. Okay, what about I to the seventh? That's the same thing as I to the sixth times I to the first. So negative 1 times I, which is negative I. Okay, and then what about I to the eighth? Well, that would be the same thing as saying I to the fourth times I to the fourth, which is positive 1 times positive 1, which is 1. So to recap, I to the first was I squared is negative 1, I to the third is negative I to the fourth is positive 1, I to the fifth is I to the sixth is negative 1, I to the seventh is negative I, and I to the eighth is 1. So if you see here, this pattern is repeating every fourth part of the pattern. I, negative 1, negative I, 1. I, negative 1, negative I, positive 1. This pattern repeats every multiple of 4. So if you're given I to any power, you can find what it is by dividing the power by 4 and finding the remainder. So let's practice that. Here on example set 2, part A, I have I to the 20th. If I divide 20 by 4, I get 5 remainder 0. If my remainder is 0, that means that it's going to go all the way through the pattern and end on the last term, which is positive 1. So I to the 20th is 1. Let's look at B. I've got I to the 27th. If I divide 27 by 4, I'm going to get 6 remainder 3. My remainder is 3, which means I'm going to land on the third part of the pattern. 1, 2, 3. The third term in my pattern is negative I. So I to the 27th is negative I. On C, same thing. I to the 33rd, if I divide 33 by 4, I'm going to get 8 remainder 1. My remainder is 1, which means I'm going to be on the first part of my pattern. So I to the 33rd is I. Okay, last one. I to the 97th. If I divide 97 by 4, I get 24 remainder 1. So again, my remainder is 1, which means I'm on the first part of my pattern. So I to the 97th is I. If my remainder had been 2, I would end up at the second part of my pattern, which is negative 1. So again, the pattern repeats every multiple of 4. I, -1, -I, +1. So if you're given I to a power, all you have to do is divide that power by 4, find your remainder, and locate where in the pattern you have ended up. Okay? And that concludes our notes today on complex numbers.